Okay, so I want to talk about cooling slash heating. Really should be warming slash cooling, I guess. Note, this does not apply to phase, and this is, yeah, it's not.
The phase change when you go from solid to liquid?
Yeah, so what I want is in a phase diagram. You guys all seen a phase diagram?
Today, actually.
Okay, so normally they go, this one's usually temperature on the X and pressure on the Y, I think.
Yeah.
Okay, so down here would be cold vacuum, right?
Absolute zero vacuum.
And up here would be cold and not vacuum, right? And over this way would be hot vacuum. And up here would be hot and smashed, right? So someplace in this diagram, and I am not a chemist, so I'm going to draw this like this. And this is not what a phase diagram looks like. There would be something like liquid goes in this part, and solid goes up here, and gas goes down here.
Is that like per substance?
Yeah, so there's a phase diagram for most. Yeah, I hesitate to say anything about chemistry, except that I've seen pictures like this that mean things in chemistry land. So, what my heating and cooling doesn't apply to is phase out of the appropriate phase, right? So yeah, it doesn't apply to things undergoing phase change. So when we brought our liquid nitrogen in here, right? That was as a liquid, right? But it was really definitely down here in its like, yo, I want to be a gas area. You guys see that? So most of the energy in the room wasn't warming up the liquid nitrogen, because the liquid nitrogen isn't getting any warmer, it's boiling. Okay, see that?
So at that point you need latent heat and vaporization like everything else?
Yeah, I need to do some calculations about how much energy it needs to absorb to vaporize and then kind of discount for that. What Newton's law of heating and cooling does do is like if you have a coffee cup set out, you can figure out when it's going to reach 5 degrees above room temperature really easily. Please note, it also, we talked about this at the beginning of the semester, it also doesn't do things like if you bring a cubic meter of liquid lead into this room, it won't work. Because a cubic meter of liquid lead is going to heat this room to the point where the ambient is going to change, right? Like this does stationary ambient. So your cup of coffee is not warming up the room as a whole, right? But if you brought in 1,000 gallons of coffee in here, it might appreciably warm up the room. You guys with that? So, doesn't apply to phase change. Also not if ambient is changing. And we worked out some way at the beginning of the semester to like fiddle with this to make it more like it would work. Right? Whatever. Okay. So, I want to give you the governing equation for this. And the governing equation is the rate of change of temp of an object is proportional to what?
It's current temperature.
Close.
The difference between current temperature and the temperature of the environment.
To the difference between its temp and ambient. So if you were writing this down in differential equations land, what would you write?
T prime,
T prime is,
something
A
minus something
times
times.
T minus, T root, however you want to know that.
T-
TA.
T sub A.
perfect. Cool.
Do the order of those two internal T's right there matter?
You mean this or that?
The T and the TA? Will that just,
You can think about it this way. So if T prime is positive, right? You guys see that? Like if the temperature's going up,
oh, the TA is bigger?
then that would kind of imply that the temperature of the object minus the ambient is positive. That would be the object's warmer than the room. Oh, that's like backwards, right?
Say for negative.
You guys see that? So where's that getting absorbed in here? Because it doesn't actually matter.
And it's on.
T.
It's in this constant of proportionality. So you should think to yourself, right? Like, think to yourself, T bigger than T ambient, right? If the object's warmer than the room it's in, what's it going to tend to do?
The rate will be bigger.
Yeah, it's going to tend to cool, right? Okay, so if I was being more honest, maybe I would slap a minus on that K. Is it necessary for the math? No, not at all. Is it a good thought? Yeah, for sure. Okay, so let's do an example. I think we did this the first day, by the way. You all remember this?
Yeah.
Today feeling easy? Okay, good. So I would like to do beer. This is the most relevant spot in my life for this. When you take a beer out of the fridge, how warm is beer in the fridge?
Well, how cold is yours?
Yeah.
40 something degrees, It's a cool beer.
Yeah, so fridges should be under 40 degrees, and 35 is a common setting for fridges. Mine's actually set at 37 because I don't really care about food poisoning. I have an immune system, but whatever, set your fridge at something. 35 is what I have written down in my example.
If you're in Fahrenheit, yeah.
So here's 35. Oh yeah, and we should be noting, right, that this is Fahrenheit, not centigrade.
35.
Or Kelvin. If it's Kelvin, your hand's really gonna cramp on that and you're gonna have phase change problems.
If that's the fridge, then the freezer's really cold.
Okay, so anyway, I have observed that beer goes from truly cold to kinda cold, right? Like 35 degrees to 40 degrees in about 3 minutes.
You gotta act fast.
Yeah, exactly. So, then the question becomes, if I forget about it, which happens because you guys have met me, if I open my beer and leave it sitting on the counter and walk away for 20 minutes, how warm is it?
Are you going to make T prime temperature for the second and temperature for that? How would do that?
I don't know. I'm going to make it temperature per whatever's here. I don't usually think about those considerations before I start doing problems. I think about them afterwards. But yeah, that's a good thing to think about. You might want to consider what units you're putting in.
Which, as I recall, you should probably keep it whatever you did.
Yeah, so I'm going to keep my temperature in degrees Fahrenheit. I'm going to keep my, what else here? I'm going to keep my time in minutes. Because that's what I was given. So that's what the person who asked this question is going to understand. Right? You don't want to answer them in Kelvin. Because they'll be like, huh? Well, and by the time you finish this problem in Kelvin, they'll have already had too much beer. So. Okay, anyway, point is, how do I do this? Like, what am I doing? Oh yeah, I need to know what the temperature of the room is. You guys see that? What's the temperature in the room?
68.
68.
That's a warm.
I think it's 70.
It's about 62. How warm is your house, Joe?
My house is usually like in the winter, like 65, but it doesn't take 3 minutes. Like it takes a lot longer than 3 minutes for my beer to warm up at that. So I'm gonna just assume 70 degrees.
Couldn't we solve for that if we know that it went from
You
35
have to know
43
K.
minutes?
Yeah, so you need to know one of two things here. You either need to know the ambient temperature or the constant of proportionality. You might know the constant of proportionality if you know something about this liquid and or this object and how fast it dissipates heat, right? But imagine two objects. One is composed entirely of little aluminum fins, right?
Yeah.
And the other one is a solid stone with a wrapper of insulation, right? One of those is going to lose heat a lot faster than the other. Even though Newton's law of cooling holds in both cases, it's that K that's changing there. You guys see that? So you need to know one of two things. You either need to know some information about your object, which is this guy, and the temperature of the room, or you need to know some different information about your object.
Does this work out to where water K is like 1 or something?
Oh, I forget. Probably. In the appropriate units.
Yeah.
In the appropriate units, it's definitely 1. I'm not clear if those are reasonable units.
Calculus reason, I think.
Yeah, so the specific heat of water is 1,
Yeah.
which tells you that to raise a gram of water a degree centigrade, you need 1 calorie, right?
No, specific heat is 4.184.
Oh, what's the thing about?
No, you can have it.
No, it's in the other unit.
Yeah, you can have it.
Oh, then it's a weird number. I think it would
No,
be-
it's 1.
No,
It's defined to be 1.
It's one measure.
There's a set of units for which
Yeah.
the specific heat of water is designed to be 1.
How is this like grams per degree Celsius?
It is 1
Yeah.
calorie.
It's a calorie?
Kilocalorie.
Kilocalorie, yeah.
Oh, okay. Cool, good talk. Anyway, whatever. There is some set of units for which that's true. How do I do this problem?
You have to figure out what K is.
Yeah, you got to figure out what K is, right? So first things first, you should solve your differential equation. What kind of differential equation is this? Yeah, it's separable. You guys see that it's separable? What does separable mean? How many little t's you got kicking around here? Yeah. Like how many functions of your independent variable do you have kicking around?
2, if you count the prime.
2. You got t prime and you got t, right? Which is really essentially 1, right? But otherwise, there's no little t's present at all, right? So normally I'd be trying to shuffle the kind of independent variables to the right-hand side and the dependent variables to the left-hand side and then integrate. But here it's even easier than that, right? So I just get the big t's to one side and leave the k over there. So rearrange, multiply by 1 over t minus t ambient. Get yourself 1 over t minus ta times d capital T d little t equals minus k, I think. Then what? Slap some squigglies on this thing. So you should get the integral of 1 over t minus t ambient d capital T is the integral of minus k d little t. I'll do the right hand side. You guys take care of the left. Okay, so what do you need on the left hand side?
Natural log of absolute value of t minus ta.
Natural log of the absolute value of t minus ta. Okay, where'd you get that? USO? Cool, nice. All right, then what?
Slap a log eater on it.
Yeah, slap a log eater.
I'm using your terminology.
Yeah, I brought this upon myself. I fully acknowledge that. So I think I got a e to the minus kt. Yeah,
A is negative KT over C.
cool, let's do that. That's a horrible A. So I got a e to the minus kt, and then,
Does that relate at all to the ambient subscript, or is that just a?
no,
Some jackass stuff.
yeah, that's just some jackass nonsense.
Your A can take care of the absolute value,
And we can gobble the absolute value,
and push the ambient temperature to the other side.
and let's shove the ambient temperature to the other side. So we get big T as a function of little t is some constant e to the minus kt plus the ambient temperature. Does that make sense? When we think about what this is ambient temperature up or down some kind of exponential decaying function.
Towards the ambient.
Yeah, so this is going to exponentially decay towards the ambient temperature. Is that what I think beer does? Yeah, probably. If I had to draw the curve, it probably looks a lot like this. Here's room temperature, and it probably goes like that. It looks an awful lot like an exponential curve. Okay, so probably that's what's up. Okay, cool. How would I check that? You guys see, I told you that this was Newton's law of cooling, right? Like, pitched this as like a fundamental fact of the universe. Right? But,
You have to measure.
yeah, Newton's just some dude. Didn't even invent calculus.
Oh,
Oh,
That was Leibniz. So we're clear. Anyway, point is, Mr. Newton got this named after him, right? But all this is like the dumbest thing you would say about temperatures. Be like, yeah, probably the rate at which it changes is basically how far away it is. Right? Like, how do you know that's how temperature actually works?
Get some thermometers and get yourself some stuff.
Yeah.
that you can-
Get a bunch of thermometers and some warm stuff and some cold stuff and stick it out in a room and measure. Right? It turns out this is a pretty good approximation, but it is a model, right? All of this is mathematical modeling, not honest to God truth, right? Okay, how do I use that model to solve my beer problem?
We can plug in 35, 40, and 3 minutes. And
Okay.
70.
I can plug in 35 and 40 and 3 minutes to get what?
oh, you also need 70 degrees in there somewhere.
your initial.
Yeah, that's your TA.
Well, we're gonna solve for that.
Okay, so
Either A or
I know what? What does this first statement say? 35 degrees warms to 40 degrees in 3 minutes. That tells you about,
TX3 is 40.
yeah, that tells you a capital T of 3 is 40, right?
You plug all that in, you don't know, but
And T of 0 is 35,
Wait.
right?
How many unknowns are there, or how many things are there kind of unlabeled over here?
2, 3.
There's two.
There
That
are
we don't
three
really know.
things unlabeled. There are three kind of parameters in this model, right? There's an ambient temperature, there's a K that's something to do with how fast this thing warms or cools, and then there's this A, which is
We don't need that.
something about where it starts, maybe, best guess? Okay, so I think I know T of 3 is 40. That's this part. What's the 35 degrees part? What's that?
T of 0.
That's T of 0 is 35.
It's gonna be A too, isn't it?
Yeah,
It's going to be close to A.
it's gonna be A plus TA.
And then, what's the thing about the room?
That's for TA.
Yeah, that's kind of what happens as you send T to infinity, right? You guys see that? Oh, yeah, that's going to be what the ambient is, right? Because the e to the whatever will drop off of there. You guys see that? So one way you could look at that is as T of infinity. Another way you could look at it is just to say, hey, you built your model to make that 70. Or you made that TA in your model. So I think I know these. I know TA is 70, so I could plug that in. T of 3, right, is AE to the minus K times 3 plus 70. That's my kind of first statement. T of 0
A plus TA.
is A plus 70. Oh, but that's supposed to be 35, right?
Yeah,
So what's 35? Or what's, sorry, what's A?
-35.
Negative 35. You guys see that? Okay, so I could go back in and be like, okay, so that's negative 35, that's negative 35.
Solve the K now.
Oh, hey, now I know what K is, right? You guys see that? So in that first equation there, I've got 40 equals 35 e to the minus kt plus 70.
Net negative 35.
Negative 35. Thank you.
And then T would be 3 right there if it's equal to 40.
Maybe 3K.
Don't know what I would do without you guys. Thank you. Okay, now I want to solve for k, right? So you subtract your 70. So you got negative 30 is negative 35 e to the minus 3k. Then what? Close.
35.
Divide by negative, put a negative 35 meter on there. Right, multiply both sides by negative 1/35. So you get 30 over 35, which is some fraction that we could maybe deal with on a better day, is e to the minus 3k. And then what should we do with this?
Eater.
Yeah, log both sides on this one. So we got k is the natural log of
6/7 divided by
natural log of 6 minus the natural log of 7 all over negative 3.
Yeah.
Algebra. Cool. Okay. Somebody give me an approximation for that.
Positive.
Positive, is that what you said? Yes, I designed it to be positive. That was that whole rigmarole at the beginning about do I make k negative or positive or what?
Positive.
But thank you.
My
Yes.
calculator's not yours.
First ballpark, positive. Next ballpark,
0.05.
0.05.
Yep.
Yes, they are.
Okay, cool. Now, what do I use that information for?
Equation.
Okay, that's what k is. So now I want to know about 20 minutes, right? So where do I go for 20 minutes?
You build your actual T.
Oh, no.
States you solve for.
Okay, so now I know things about my T of t equation, right? And I want to know about T of 20. So I know A was minus 35. Then I got an e to the
negative 1/20
negative 1 over 20 times 20 plus
It's 37%.
70. Okay. So I got negative 35 times e to the minus 1 plus 70. Which is very carefully orchestrated to be about negative 10 plus 70. Negative 12 plus 70. Better approximation. How big is E? Oh my god. Quick.
2.71828.
2.7 something.
Uh,
So I'm going to get
66.5 years.
7.12.
so like 57.2 degrees, maybe?
Well, I used to fold out of these, so maybe.
Did you put,
I just want you to calculate.
you get a divided by E?
I put times e minus 1. Or negative 1.
Oh, that's it, 10. This button on your calculator, this thing, is exponential notation. That's a 10 to the.
82.8.
What? Negative. It better be below room
It's
temperature.
Well,
If you leave your beer out and it warms up to past room temperature, get a new house. Like, just leave. That place is haunted as shit. Just don't drink the beer, just leave. Cool? Questions? Things? You guys kind of with this? These models should be really easy, right? The only thing about these models is you have to go through all this rigmarole of calibrating the darn thing, right? Okay.